In this video, we shall be solving certain problems based on Cauchy's integral formula. To begin with, let us take a simple problem. Integral, we have to evaluate this integral. E raised to x, z minus 2, this is 2, and into z plus 4, dz. This is to be evaluated along this curve C, where C is circle, circumference of a circle of radius 3 units. Now, this situation can be shown here. We have a circle centered at the origin. 1, 2, 3, 3, minus 1, minus 2, minus 3, and so on. Similarly, you have 1, 2, 3, 3i because it's imaginary axis, and minus 3i here. And now this circle is to be traversed in anti-clockwise direction. So let's do one thing. First of all, before we go for this solution, we must realize that we have to follow a certain procedure. The procedure that we will be following will have the first step. The first step of our procedure will always be to examine this function, the given function, for any singularities, to see whether it has any singularities or not. As you can see, its singularities, there are two singularities. Z is equal to 2, that will create a 0 here. Z is equal to minus 4, that too will create a 0 here. So it has two singularities. So let us write here this singularity, and then one more thing. We have singularity, and we are going to write something more, but let us wait for a minute. Singularity, Z is equal to, first singularity, Z is equal to 2. Second singularity is Z is equal to minus 4, because you have to take this Z plus 4 equal to 0, that gives you Z equal to minus 4. This singularity. Next thing that you will check about these singularities is whether any of them is enclosed by this C or not. So you have another this column here where you will check the states of these singularities. States, by states we shall mean whether this singularity occurs within this curve or not. Let's see, Z equal to 2. Is Z equal to 2 within this? Yes, exactly. Here is 2. Here is 2. And so Z is equal to, this singularity is within this C, within this curve C. It is inside the curve. Whatever Z is equal to minus 4, that is outside. Minus 4, that is outside. Now this is this singularity. Singularity will be shown by a cross, a dangerous sign. Say similarly here, singularity. We won't bother about this singularity at all for obvious reasons. It doesn't concern us. It is outside your this chosen path. It is outside that. But this singularity is our concern. Now, since this curve has one singularity, so we can directly apply Cauchy's integral formula to its solution. Now, I want to apply Cauchy's integral formula. See, Z. I will be bothered only by this. Stats means whether inside or outside. Z equal to is inside. Inside. I stands for inside, and outside. Only this is our concern. This is not a singularity for us for this loop. So what I will do, I will treat this Z minus 2 as the singularity factor. I will not treat this as singularity factor. I will absorb this Z plus 4 with e raised to x. So I will write this relation, this integral like this. I will write this: I is equal to integral C, then e raised to x divided by Z plus 4 z plus 4 into 1 by z minus 2 dz. See, I have collected these two here because d is this e raised to x divided by z plus 4 does not have a singularity for me for this loop. So this is what we write as fz in this Cauchy's integral formula. This is here Cauchy's integral formula. See, fz divided by z minus a, a is singularity dz, and that is equal to 2 pi I fa. That means value of this function fz at a. This fz is here e raised to x plus z plus 4. Fz is e raised to x divided by z plus 4. And where is z minus a? Z minus a is here. This is z minus a. The singular, we will call this singularity factor. The singularity factor is here. So treat this as fz, and now solve this using this formula. Here is, it becomes so simple. Now we have the integral, given integral is this. Going back to this is given integral. Integrals, loop integral c, then 1 second back, e raised to x divided by z plus 4, e raised to x divided by z plus 4. Just separate only that factor which is singularity factor. Rest is fz. Other than the singular factor, rest is fz. So e raised to x divided by this, and then we have 1 divided by z minus 2. This is the singularity factor, z minus 2 and dz. Now it is, when we compare with this Cauchy's integral formula, we have, according to that, Cauchy's integral formula tells us that fz divided by z minus a dz is equal to 2 pi I fa. Now applying this formula here, I have I is equal to fz. Fz is this integral e raised to x divided by z plus 4. This e is this fz divided by z minus 2 dz. See, that is, this is equal to, since this is fz, this much is fz, and this is z minus a, so I will write its value equal to directly 2 pi I fa. That means value of this function at a, e raised to x divided by z plus 4, value of this function at z equal to 2, because a is 2 here. A is 2 here. Okay. Substituting this value then in it, I get 2 pi I into e raised to 2. It must be z. Sorry for this. It is e raised to z, not this e raised to x. E raised to z. Coming back, it is e raised to 2 divided by 2 plus 4. 2 plus 4, that is 2 pi I into e squared divided by 6. The 2 3s are, that is pi I by 3 e squared. This is the answer. So what was our method? Our method was, we first checked this given this integrand, checked it for any singularity, and then after detecting singularities, we then watch for those singularities which fall within our this given curve, closed curve, and for those singularities we apply this Cauchy's integral formula, and then things are quite obvious, quite easy, simple and easy. Let us go ahead for another problem, and this problem that I am now going to show you is a very, very important problem, because it is going to tell us something. Suppose we have now, suppose the situation in previous question, the situation was that we had just one singularity inside our C. So since there was one singularity, hence no problem. Cauchy's integral formula could be directly applied. In this, that the problem that I am now showing, we will be having two singularities inside. And in that case, what can we do? The simplest thing to do in this case is that we have to replace this curve by two curves, enclose each singularity. Each singularity is to be enclosed within a circle. Within a circle, enclose these within circle, and then apply Cauchy's integral formula to this separately, and add up the results at the end of this solution. Add up the results that will give you this total integral, the answer. But there is a question: can we do this thing given the fact that this is a singularity, this is a singularity? Well, the this question that I am now going to solve, that will explain to you that we can do it. Why can we do it and how can we do it? Let's see. Let us go for that. So here is the question. Question is, we are given an integral. Integral, it is cos z divided by z plus 2 into z plus 2 into z plus I into z plus z minus 2I dz, and path of integration is this. This is the path of integration. Look here. It is, say suppose this is 1, 2, 3, 1, 2, 3. So 1, 2, 3, 1, 2, 3, and so on. The path passes like this. Is a rectangular path that passes like this and this, and then this. This is the path. Let us call it C. A rectangular path along which we have to integrate it. And given this path, how to integrate it? This is y. So this is y and this is x. How to integrate it along this path? Let's see. We know that we can deform this, provided we can deform this into another this curve, closed curve, provided the function fz is analytical between this and that new curve. At every point it is analytical. Let us first check this. To begin with, the first step always should be this: to check the given this integrand for singularities. So here we have singularity and stats. Singularity is, for example, here z plus 2 is equal to 0. If you put this equal to 0, z will be equal to minus 2. This is one singularity. Z equal to minus 2, sorry. Z equal to minus 2 is first singularity, for example. Z equal to minus 2 like this. Minus 2, it is z equal to, let us show it explicitly, z equal to minus 2. Then there is another singularity, z is equal to minus 1. Z equal to, sorry, z equal to minus 1. Z equal to minus 1. Z equal to minus 1. Let us write it here. Z equal to minus 1. Z equal to, first was z equal to minus I. It is z equal to minus I. Then third is z equal to z plus 2i plus 2i. Let's check whether these are inside this given curve or outside. Let us look for this z equal to minus 2. Z equal to minus 2, it is outside. Minus 2, minus 1, outside. Then z equal to minus I. Minus I, that is here. Minus I. This is singularity within C. Then z equal to 2i. Z equal to 2i. 1 and 2. 2i. Again singularity 2i. So there are two singularities within this. And now, what can I do? How can I deform this into another path which will be such that the region between these two paths, at every point in that region, our function is analytic. Along with the two paths. What does that mean? Let's go to here. You have this. This is your original path, and these are two singular points. One is here, singularity, another is here, singular. Now imagine I deform this path, and then can I change this path? Say C. Can I change this path C into this path? C dash, say for example C dash? Yes. Why? Because this region, the region between these two paths, at every point of this region, the paths are the function is analytical. It is not analytical only at this point and this point. Rest of the points it is analytical. Now I will deform it slightly more. I will then change it into this. This is the original path, and then what I do? This is one singularity. This is another singularity. What I do? I enclose this singularity by a almost a circle. Then, but I will not end the path here. Then I go here and enclose this by a circle. So two circles. This is anti-clockwise. Here we have this anti-clockwise, 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 anti-clockwise. Let this be this path. Let the different sections of this path. Well, is this path allowed? Yes. Why? Just a minute. You will excuse me for a minute. So these two paths, they are allowed. This is allowed because see these points. Look at these points and all these points. The paths are this function. Our function is analytical. At all these points, our function is analytical. Now, having said that, we can further see. We can do one more thing. We can further squeeze them. In fact, these two branches of the path, this branch and this branch, these two branches, we can imagine them to be coincident. See, it is like this. The final version I will be showing here. This version, it is like this. If you look at this path, this deformed path, this section of the path, let me show this section. Let me call this C1. Let me call this C2. Let me call this C3. Let me call this C4. Now, integral along C3 and integral along C2, they are in opposite directions. Hence, in the final case, they will cancel out. So this means that this piece of the path is not relevant to us. So ultimately what happens, we can, since we can squeeze this more and more so that this end and this end, they come closer and closer until this is reduced. These two are reduced to a single line. these become coincident. These are reduced to a single line, and that single line can be done away with because its contribution is cancels out. In one direction, its contribution is positive. In another direction, its contribution is negative. It cancels out. This justifies our original assertion that we can enclose this bias path here. We can enclose this separately by a path here and then apply. Now this is a path which is smooth or at least piecewise smooth. Along this path, this function fz is our function is analytic, and inside this analytic path, inside this analytic function, this curve, let us say curve C1, inside this there is a singularity, so we can apply Cauchy's integral formula. Similarly, we can apply Cauchy's integral formula for C4. So our procedure is something like this. We start with this. We say we can say, so suppose for total integral. Our example is, say we have cos z divided by z plus 2 into it is cos z plus 2 into z plus I into z minus 2i dz. This integral, if I write I for it, then this total path C can be deformed into, it can be replaced by, it can be deformed into this path. I have the integral, I have along C1 plus C1 plus C2 plus C3. These are four parts of this path. This integral will be simply equal to integral along C1 plus integral along C2. I am not showing the integrand. C2 plus integral along C3 plus integral along C4. Out of these, C2 and C3 will cancel out. These will cancel out because they are evaluated in opposite direction, hence they will cancel out. Now, when they cancel out, these two cancel out, we are left with this integral C1, integral C1 plus integral C4. So we will treat as if we have to separate these problems. In one problem we have singularity here inside this, in another problem we have singularity here inside this. Now it is quite easy to evaluate this integral. Integral is, we will start with this. Let I be equal to cos z divided by z plus 2 into z plus 1 z plus I into z minus 2i. Let me take first, let me go back and tell you one more thing. That is, what I will do, I will take first this integral, only this integral, C1 integral, C1 integral, and then I will take up C4 integral. At one time, let me go for one, till you develop confidence, and then as you develop confidence, then you can handle both of them simultaneously. So let me go for this C1. Let me forget about everything and focus on this, only this, what is it, singularity. This singularity is, as you know, this singularity is, let us check which singularity it is. It is 2i. So this is 2i singularity. 2i. Let's focus only on this and calculate this integral. I1 is equal to what was the name of this path? Let us go back and see C1. So it is C1 cos z. Now what we do now? We rewrite this in such a way that we separate this singularity factor. Singularity factor is this. z minus 2I is equal to 0, that gives us z. This is singularity factor. We make it denominator and rest of it numerator. That is cos z divided by z plus 2 into z plus I whole divided by z minus 2I dz. It's not necessary that you write like this, but it helps you to compare it easily with this fz divided by z minus a dz. You compare it with the Cauchy's integral formula and write. Then you write 2 pi I fa. Sorry, 2 pi I fa. 2 pi I fa. So what is fa here? Fz is here. Leave this this singularity factor separate, and rest of the function fz is here cos z divided by z plus 2 into z plus 1, because although these two are singularity factors, but not for this path, not for this path. So we treat it as this. What is the value of fa? What is the value of this fz at a? What is a? A is this 2I. Is this 2I? This singularity 2I. So we have fz is equal to cos z. It is 2I cos 2I divided by z is 2I plus 2 into 2I plus I. 2I plus I. So cos 2I, now see. Cos 2I. You can check for this its formula. It is hyperbolic cos 2. 2I, it should have z. Sorry, z. Cos 2I z. No, it is only cos 2I. Cos and z, value of z is to be substituted, that is 2I. So that is why it is cos 2I. Okay, right? No problem. Then we have similarly here. This is the situation here, and then we have okay. I'm a little bothered by this cos 2I alone. We have cos 2I. Is it that means this cos 2I? It is basically it's a number. Okay, let's leave it for some time. Till I come back to this. This is one of the integrals. Yeah, I have evaluated it. Yes, I just evaluated value of fz at a at this. I should say 2I. I have evaluated it at 2I. It is okay now that according to Cauchy's integral formula. Now you can easily tell me what I1 will be. I1 will be simply fa. Fa is this much cos 2I divided by 2I plus 2 into 2I plus 1, that is 3I into now the rest of the value. This is fa. What else is there in Cauchy's integral formula? 2 pi I fa. Fa I have got. Now 2 pi I. So we have this I1, value of I1. Similarly, we now, in order to find value of I2, I will take this singularity now. This singularity. How much was this singularity? Let me check. It was this next singularity is one is z equal to I, another is z equal to minus I. This z equal to minus 2, this outside our this curve, original curve. So this is the singularity, and the circle that I have chosen here is C4. It is minus I, z is equal to minus I. Okay, now once again this is I will call it I2. I2 is equal to integral C. What was the original integral? It was cos z divided by z plus 2, z plus I, z minus 2I. Cos z divided by z plus 2, z minus I, z minus 2i, z plus 2i. Let me check. Z minus 2i plus I. This is plus and this is minus 2i dz. Now we are having this C4 as our path, and this within this C4 there is just on this singularity z plus I. These two are not singularities now. They will be absorbed in cos z, and the whole they will become fz now. C4 cos z divided by z plus 2 into z minus 2i, leaving behind the singularity factor. Singularity factor is z plus I dz. Now you develop this, feel what is happening. This is fz. Fz here is this cos z divided by z plus 2 z minus 2i. Just remember that fz is whatever is left after the singularity factor. Singularity factor is this. How do I know it is singularity factor? Because I am considering here singularity minus I. Why from that minus I come? It came when we put z plus I equal to 0. So this is singularity factor. Rest of, keep singularity factor separate. Rest of whatever integrand you have, that is fz. Now fz is to be, it is to be evaluated at the location of this. What is its value at this location? Let us see. F minus I is equal to cos minus I divided by z minus I plus 2 into minus I minus 2i. So this is cos. If you have minus with cos, it is simply absorbed. Cos I divided by 2 minus I into minus 3i. Now this is the value of the function at the location of this singularity. Next, what else is there? Yes, next it becomes easy now to use Cauchy's integral formula, and that is Cauchy's integral formula is this: C fz divided by z minus a dz, that is equal to 2 pi I fa. Now this means, therefore, integral back to this integral. This is our integral. Cos z divided by this. We should write it like this: cos z divided by z plus 2. Yeah, z plus 2 into this z minus 2i divided by z plus I c4 is equal to 2 pi I. Here is dz. 2 pi I into fa. Fa has been actually calculated. It is cos I divided by this. Cos I divided by whatever it is. You can now tackle that yourself. That's 2 minus I into minus 3i. 2 minus I into 2 minus I into 3i and into minus 3i. And lastly, what will be the total integral? That will be simply I1 plus I2. This is the procedure. So simplification I will leave to you. You can do it yourself. So you can see how we use Cauchy's integral formula. Now there is now one more. I have to show you one more example that is based on this Cauchy's generalized. It is generalized Cauchy's integral formula. When that is involved, when do we need this? We need this if any one singularity has a power other than 1. For example, if in our suppose this question that was given to us, if we had something like this: cos z divided by z plus 2 whole square z minus 2i into z plus I. If we had this square here, we cannot directly then apply Cauchy's integral formula. This can be handled with generalized Cauchy's integral formula. How we can handle it? Let's take an example. We will first go for a very simple example that will be quite simple for you. For example, suppose you have to integrate this. You have this integral c e raised to z divided by z cube. Now dz. Where is the, does it have a singularity? Yes, definitely. That is z equals 0. If you put z equals 0, it will, this function will blow up. Now, so this is a singularity. It is, of course, it is not shown in the form that we are already familiar with, but we can recast it like this. We can write I is equal to integral c e raised to z divided by z minus 0 whole cube dz. Now you can see there is a power other than 1 on this singularity. Yeah, what we do in this case? We apply Cauchy's integral formula in the generalized form. That is generalized Cauchy integral formula. We will have to keep that here. Suppose we have this. This is the Cauchy generalized integral formula. That is fz divided by z minus a raised to n. If it is n plus 1, suppose it is n plus 1 dz, then you will get call this n plus 1, this denominator, then you will get fn. You have first this factor 2 pi I divided by n factorial fn fna. This is what we deduced in our last lecture, generalized Cauchy's integral formula. And when we take this generalized Cauchy integral formula, see here, if you compare it with this, what do we have? We have here e raised to z, fz is equal to e raised to z. Okay, so fz is equal to e raised to z, right? Number one. Number two, z minus 0 is equal to 3. So the power here is 3. What will be then power on this side? It will be 2. This means that we will need second order derivative of this fz, and at the location at this a, that means at 0, value of that. Let me explain this. What is fz? That is ez. Let us differentiate it for first time. F dash z is equal to e raised to z. Simply let us differentiate it again. The e raised to z. Very good. Let's calculate its value. Now at a, what is a? 0. So f dash 0 is equal to e raised to 0 is equal to e raised, sorry, just a minute, e raised to 0, sorry, so it is pen. Okay, e raised to 0, that is equal to e raised to 0, and e raised to 0 is equal to 1. So you have got this. You have to differentiate this, what, this fz twice without this factor. Do not, when you differentiate, do not differentiate this. You are differentiating this. Now, after having done that, now it is quite easy. Now you can write easily its value. Let me write it here itself. Once you understand something, then things become quite easy. So you have, this is the value of this 2 pi I by n factorial. Now what is n? N is, it's not this, not n. This n plus 1. You can check it. It's n plus 1. It's not n. And this is one of the mistakes that students commit. It's not 1. It is to be reduced by 1. Then it becomes n. So this is 2. N is 2 factorial. Then you have fna. I have written I. Now fna. Now you have the second factorial. Second derivative of ez. Second derivative of ez evaluated at a, that is 1. So our answer is 2 and 2 goes. Our answer is pi I. I hope that you have been able to understand all this. You can now you can develop this I mean, you can develop practice. You should rather practice more and more problems so that you develop confidence. Confidence is very, very important. Let us go for one more problem before we finish this lecture. Let's go for one more problem. Suppose I have this integral. I have this integral. It is integral z plus 1 divided by z into z minus 2 into z minus 4 whole cube dz. So so the moment I look at it, I am convinced that I will have to use not Cauchy's integral formula, rather I will have to use generalized Cauchy's integral formula. Generalized Cauchy's integral formula. Now, I let me keep that written again here on this side. I will write that. I have just used that here. It is this. uh, you must keep, it is better for you to keep till you remember these things. You must keep it written on some page of paper. Keep it when you are solving problems, keep it in front of you, because you need not then turn pages or look for these formulas. Keep them with you, and on some separate page of paper, and then go for these solutions. Do you have we have this, like me, you will not then require to go back and back. Integral c, integral f z divided by z minus a whole raised to n plus 1 dz is equal to, and it is equal to, let me see, what is 2 pi I by n factorial, 2 pi I by n factorial into once again I go back into fna. I would suggest you to do, when you have, the moment you realize that you have this you have to use generalized these Cauchy's integral formula. The moment you see it, just first recognize what is your fz. Look at this, for example, suppose this is n plus 1 here, sorry. Now look at this. We have there are three singularities. One singularity is equal to, these are singularities. Let me see. Singularities, singularities, and this is their states. First singularity is z equal to 0. Second singularity is z equal to 2. Third singularity is z equal to 4. But this is multiple singularity with order higher than 1. Okay, now states means whether they are within our. I have not actually spoken of which what is our this I mean integration path. Given integration path is z minus 3 equal to 2. That means it is path is circular with radius 2, but the path is not centered at the origin. It is shifted from the origin, and it is centered at 3. It is something, it is like this. 1, 2, 3. It is centered at 3. This is 3. So it is a radius that is equal to 2. So from 3 it will go to 1, and here it will go to 5. From 3 equal go to 5. This is 4. This is 1 plus 1. Now this is our path. Okay, we have this now. See, we have yes, let us do this thing now. Z equal to 2. This is z equal to, first of all, let me see which of the singularities within this. Z equal to 0, no, outside. O means outside, so this is not of my concern. Good. Z equal to 2. This is 2 here, 2 here, This is the cross that I showed here. Inside, inside, z equal to 4. Inside, both are inside. So one is outside, the two are inside. Now, regarding this z equal to 2, I will actually use now these circular, these paths. My strategy will be this. My strategy will be, sorry, what is this? Sorry, let us go back to this. Yes, my strategy will be to use this. This 2, this is 2. I will show it like this, and I will enclose with it a separate circular path. We can do that. That is C1. Then I consider this 4. I will enclose it with a separate path C2. Regarding C1, so far as C1 is concerned, when I go for C1, singularity factor is this, z equal to -2. This is singularity factor. Identify the singularity factor, that is z -2 for this. Now, rest of it is fz. So for this, let me write it. For this fz is for this. Fz is z plus 1 divided by z into z minus 4 raised to 3. So this is for C1. Now for C2, when I go for C2, what is the singularity factor for C2? It is z minus 4. So what is the fz? The function, the part of the integrand that is left without this. Now fz is equal to z plus 1 divided by z into z minus 2. Now you know what you have to do with this. You know what you have to do with this. With this C1. This is a path. It encloses only one singularity, and that is simple singularity. It does not have power other than 1. It has on one power, you can see z minus 2 equal to 1. Now, but so you can easily you have to apply Cauchys integral formula. Cauchys integral formula to this simple version. Regarding C2, you have to apply generalized. Why generalized? Now you can easily understand why generalized, because it has this a singularity that has a power other than this. This a singularity of higher order. Higher order means more than, order power having more than 1. Now for this you need this, and for this you need simple Cauchys excuse me, you need simple Cauchys integral formula. So let us do it now. We go here. We have one. Let me first handle this. Our two these singularities are these. I will show them here. One singularity is here. That is 2i. Oh, let me see what is this. It is 2, not 2i, 2. It's 2. And I will enclose it with this curve. Apply Cauchy's integral theorem to it. I have the integral is, my integral, the given integral was this. What was the given integral? Z plus 1 divided by z into z. Okay. Z plus 1 divided by z into, sorry, z minus 2, z minus 2 into this z minus 2 into z minus the last z minus 4, z minus 4 whole cube dz. integral this c. Let us write it c1, for example, c1, and let us separate fz from the singularity factor. Singularity factor and fz ought to be separated. Z plus 1 divided by singularity factor is this. Mark this singularity factor because singularity is 2. That is this is the singularity factor. Z into z minus 4 is 3, and singularity factor is to be written here, z minus 2 dz. So this is fz. Compare it with the Cauchys integral. Sorry, I sometimes call it Cauchys. It is because of Gauss's that effect. Now these great mathematicians, they are sometimes they surprise you. Uh, what sort of stuff they were? God made them. One cannot help but praising them. Anyhow, let's go back instead of getting emotional. Now, fz, we have fz divided by z minus a dz is equal to that is equal to 2 pi I fa. So you have to find first fa. So fa is fx is fz is z plus 1 is equal to z plus 1 divided by z into z minus 4 raised to 3. A is the singularity. A is the singularity. Look, what is the singularity? 2. That is f2 is equal to 2 plus 1 divided by 2 into 2 minus 4 raised to 3. That is equal to 3 divided by 2 into minus 2 cube. Minus 2 cube. That is 3 divided by 2 into minus, this will be minus 2 cube is 8. That is 3 divided by 16. Minus 3 by 16. So f2 is this. This is f2. What is now left? Not much. We have now this value of this integral is, if I show it like this, the value of integral is, I will write it here, 2 pi I into fa. Fa is minus 3 by 16. One part gone. This is one part. Another part now. Another part is this. We have another this what we call it, singularity, and this singularity has higher order. It is higher order singularity. This is z minus, the singularity is z minus 4. Z equal to 4. Z equal to 4. Z equal to 4. Okay. And let me take this as my, say, this this I should call it Gaussian surface, Gaussian path. Okay. Now let me denote it by C2, and since this is of multiple, it has power greater than 1, so I will have to use generalized form of this Gaussian integral formula. That is generalized Gaussian integral formula. That is this. That formula is this. Integral fz dz divided by z minus a raised to n plus 1 dz n plus 1 dz is equal to, that is equal to 2 pi I divided by n factorial into fna. I hope this is of course this is what we call generalized Cauchy's integral formula. Now apply this here, and for that, the most important thing, when you apply this, do one thing first that will actually help you a lot, in the sense that you won't commit many mistakes. It will save you from making mistakes. You have sorry, let us take what is n here. What is n here? N is here, the denominator has z a, let us see, the power of this z minus 4 is 3. This means this is n plus 1 is 3, n is 2. So let me do one thing. What is that? First of all, let me write fz. Fz is that part of the integrand which is left without this factor. That is here. In this case, it is you have to leave this about because it is the singularity factor. The rest is this z divided by z divided by z. It was z plus 1. Z plus 1 divided by z into z minus 2. Z minus 2. Yes, this is absent. And see, I have actually left the singularity factor apart, and rest of it is called fz. So fz is then here. I have to differentiate it two times. F dash z is equal to, now if I first let me simplify it a little, z plus 1 divided by z square minus 2z. So if I integrate it, differentiate it, sorry, I have u by v formula. U, that is z square minus 2z into derivative of this, that is 1 minus, then next you have this z plus 1 as it is z plus 1 and derivative of this now 2z 2z minus 2 2z minus 2 divided by z square minus 2z whole square. So this is it. I have to substitute since z is equal to 4. I have, no, not yet. First I have to find the second order derivative. First let me then simplify this. Z square minus 2z minus, let us see what it is. You have z into 2z, that is 2z square minus, because of this, z into 2, that is minus plus 2z. And then I have minus 2z here. Then I have minus 1 minus 2, that is 2 plus 2. Then I have divided by z square minus 2z whole raised to 2. You have here 2z and 2z, they will cancel. They are cancelled. You get z square minus 2z square, that is minus z square these two are now they have been actually accounted for by this. Then we have minus 2z and we have plus 2 as well, plus 2 divided by this z square minus 2z whole square. Then I need f double dash z. That means again I have to differentiate it, and I will get this z square minus 2z whole square into this minus 2z minus 2, this is 0 minus, then minus, I will write this piece is important, so I will write it here is equal to 2 pi I divided by n factorial fn a. Now you have minus, then we will now differentiate. We will first write this minus z square plus 2 minus 2z minus 2z plus 2 into derivative of this is minus 2z minus 2z minus 2 z minus 2, rest it is 0 divided by z square minus 2z. Of course, I would like you not to try to simplify it, because you ultimately you have to find value of this derivative at z equal to 2, z equal to 4. So simply put 4 in place of z. And if I do that, let me see what I will get. I will write that here. Otherwise, I will have to first write it on the other side and then substitute it. So I have this 4 square, that is 16 minus 2 into 4. 2 into 4, that is 8. 16 minus 8, that is 8. Then square. 8 square is 64. Then into into minus 2 into 4, minus 8, minus 2, minus 10, minus 10. That is 600 minus 640, minus 600, 640. This piece is minus 640. Now let us go to this. Minus 4, minus 8, that means minus 12, plus 2, that is minus 10. So minus 10 into this minus plus 10, plus 10, that it becomes 650. Into, sorry, there is one more. Sorry, 640, 640. We have already 640, and now counting. This was minus 10. Minus into minus 10 into, then this. Minus 2 for the 8, minus 8, minus 2, minus 10. That is 100, plus 100. Plus 100 and minus this, minus 100. This whole becomes minus 740. Minus 740. Then divided by this. Z is 4, 4 square, that is 16. 16 minus 2 for the 8. 8 square is 64. 64. Now you can check yourself how much it is. Then let's see, is it let's try with 8. No, it won't be. 8 9s are 72. No, 4 16s are 4 1s are 4 1s are 4 8s are 4 5s are. So it is 185 by 16, this value. What else I have to do? I have to then write here for this value whatever I got it, into 2 pi I by n factorial. N is 2, 2 factor 2 and 2 will go, you will get this value. So this much you can do yourself, and that's what you then see. This is how we handle this complex integration using Cauchy's integral formula, both in the simple form, that is Cauchy's integral formula in general form, and Cauchy's integral formula as generalized formula. Thank you. We will now, after this we will be going for this we will be going after Lorentz force. Sorry, not Lorentz force. It is Lorentz series and Taylor series. That will be our next topic. And after that, we will have one topic left, that is these different types of poles and the residual theorem. That we will take up in next videos. Thank you so much.